if we're asked how many unpaired electrons are in the element, what we want to do is the orbital diagram to figure out whether electrons are paired or unpaired. So manganese is element number 25. So reading off the periodic table, we would say that there are 2 electrons in 4s and 5 electrons on 3d. So when we put our 5 electrons into the d level, these are degenerate, meaning that they are the same energy level. We want to fit in single electrons with parallel spins until we fill up the orbitals before we start to pair them up. But at this point we have put in the 5 electrons that we need, so we have occupied all of our orbitals and we have not needed to pair up. We have the completely half-filled d level, so we're not going to steal any electrons from s. So we have 5 unpaired electrons. Now, if we want to rank our elements in terms of atomic size, the biggest determinant of size is whether it's left or right on the periodic table. As we go from left to right on the periodic table, we're adding more electrons into the atom in one shell. So we're not increasing the shell principal energy level, and we're adding more electrons into the nucleus, more protons into the nucleus. So the increased nuclear charge on that shell, so we have more electrons in the shell, more protons in the nucleus, more attraction between the shell and the nucleus, and it gets smaller. So as you go from left to right across the periodic table, it gets smaller, and this is a more dramatic effect than adding another shell going down a particular column. So in order of increasing size, we're going to go toward the right side of the periodic table and pick one of these first. And of these, we're going to pick the one with the smaller shell. So chlorine in level period 3, level 3 is going to be smaller than bromine. So chlorine will be our smallest, followed by bromine. So then we go toward the left side of the periodic table. We're going to look at our alkali metals here. Of course, we're going to pick the sodium, period 3, over potassium. So sodium will be next in size, and then our potassium will be the largest. If we want to rank elements in terms of increasing ionization energy, first, ionization energy is the energy required to remove an electron from gas phase atom. We like gas phase because it removes all other effects from the atom. So if we have a low ionization energy, it means it's easy to pull the electron off. So easy to make it into a cation. But we know the metals are easy to make into cations. So metals are going to have the lowest ionization energy. And then the nonmetals, well, they prefer to become anions. They rather collect an additional electron. So they're going to have a high ionization energy, difficult to pull off and difficult to turn into a cation. So obviously we're going to start off with cesium on those left here as being the lowest ionization energy. Then we go up and gallium is lower left than phosphorus, so that'll be next. And phosphorus is lower left from chlorine, so that'll be next. We're going to look at the ionization energy one more time between phosphorus and sulfur. So we look at the trend here. Phosphorus is left of sulfur, So we would say that phosphorus would have a lower ionization energy than sulfur. However, we look at the orbital diagram next. So we look at the general trends first, and we look at orbital diagrams next. And when we look at orbital diagrams here, the phosphorus has a completely filled half sublevel, completely half-filled P sublevel. This is stable. So half-filled or completely filled sublevels have an extra stability to them. So the sulfur has one extra electron to over the half-filled level. So the phosphorus is half-filled. It has some extra stability here, all the parallel spins, and each orbital have one electron. There's no extra repulsion between the pairing of electrons. But sulfur has lost the parallel spins and now has an extra electron repulsion in one orbital. So this is an exception to the general trend. The general trend would say that sulfur would be higher than phosphorus. So this is our exception. When we have half-filled or completely filled sublevels, we hit an exception. So the phosphorus is stable. The sulfur is not so stable. So the sulfur is going to have a lower ionization energy. So our higher ionization energy is going to be phosphorus, which is greater than sulfur. So when sulfur loses an electron, we'll end up with that half-filled sublevel. So it's easy to lose that electron. So it's a lower ionization energy for that electron. The phosphorus being stable does not want to lose an electron, because if it loses an electron, it loses that parallel spin stability. So it wants to hold on to that electron, so its ionization energy is higher.